please be responsive. People are not answering. I don't know what's the reason. It became a very boring class or what? There was absolutely no answering from the class. Yesterday also nobody has opened them. Let's be responsive in the class. We will end this online sessions hopefully with this semester. No other variant or no other threat comes in. I hope the next semester everyone will be back to the institute and we will resume our regular classes. In today's So in today's class, we will see flow measurement. So as a part of the measurements class, the number module 5, we are taking the flow measurement, which is one of the most important parameter that we want to measure in the process industry. So it has various applications. It many times involves cost. For example, the measurement of flow may be required to be crude in nature. That means very accurate measurement may not be required many times. But at times, for certain applications, very accurate measurements are required. For example, if you take a petrol industry, if you go to a petrol pump or a gasoline pumping station, if the flow measuring device is not very accurate, if you are supposed to get 1 liter out into the vehicle, and if you are sending every time 1.10 liters, see, it directly is involved with the cost of the material. So your capital costs will include like anything. So there are certain applications like what I have mentioned, which takes a very accurate measurement. And there are other applications where in a country like India, where we have perennial rivers and all, due to the bulk explosion of the population, now we are using water meters for every house. We are kind of controlling the amount of water that is being supplied to the houses. So there, it may be instead of 1 liter, 1.1 liter is not that costlier because we have sufficient amount of rivers, and so that is not a very accurate measurements are not required in that case. So if very accurate measurement is required, each household there are what is the population and how much cost it will be. So in such instances, we may be required to give crude measuring techniques, which will help us to measure the flow rate. So to measure the flow rates. So let me tell you. So the applications are manifolds. So we do require measurement of flow for many purposes, and at the same time, it consists of two types. One is the crude nature. One is very average measurement of the flow rate, and the other one is very precise or accurate measurement of the flow rate. Okay, so we do have many techniques, but the very basic technique of flow rate. What is flow rate, first of all? Can anyone answer me? What is flow rate or what is discharge? Let us understand that first, and then we will move ahead. Please answer this question. What is discharge or flow rate?
Sir, volume of flow per second.
The volume of fluid flowing per unit time. So that is your discharge. Okay. So meter cube per second or centimeter cube per second or liter per second. These are all the units of a discharge. So can you differentiate between mass flow rate and a discharge? What is the difference between a mass flow rate and the discharge?
So the mass flowing per unit time is mass flow rate, and the volume flowing per unit time is volume flow rate. Sir. These are two different things, volume and mass.
Mass and volume. So if I want to find out mass flow rate from if I want to find out mass flow rate, how can I find? What is the formula that I use for mass flow rate?
So rho into V equal to mass, so we can use this.
Rho into
Rho V equal to mass, or we can the density equal mass by volume, sir.
No. So what are the, can you find out the units with it? Density is mass per unit. What is what are the units? Kg per meter cube. But that does matter. What is your definition for mass flow rate? It is kg per second. You're getting
Rho
kg per meter.
AV, rho AV equal to mass flow.
So rho into density into the area of the flow into the volume or velocity of the flow is basically what we call it as mass flow rate. And area flow into velocity is nothing but your volume flow rate or discharge area into. So therefore, if you are multiplying your discharge with the density of the fluid, you will get the mass flow. So that is the relation. So whenever you want to find out the mass flow rate, you should be able to find out the discharge. Okay. So if you know the discharge and if you know the density of the fluid, you will be directly able to calculate the mass flow rate that is passing, that is happening through a pipe flow or channel or whatever. Clear?
Sir, but at certain time intervals, that density should be constant to find the volume flow rate for the mass.
In general, what we take is unless so density. What is its function basically? Density is a strong function of what? Yeah.
Incompressibility.
Density is a strong function of incompressibility. Again, yeah, it depends on the velocity of the flow. Based on velocity of the flow, your incompressibility is value to the Mach number. It depends on the Mach number, but in general, it is a strong function of temperature. Correct. Density is a strong function of temperature. Okay. So unless your temperatures varies very hugely, we generally take the density to be constant within a particular range of temperature, isn't it? So therefore, you are not at all depending on, you are generally taking the density to be constant within a certain small range of temperature. So therefore, in general, you are multiplying with the density, the discharge with respect to the density of the flow to get the mass flow. Again, if it is a steady state, it is different. If it is transient, that means if the velocity flow rate or the flow rate is varying with respect to time. So for a brief period of 5 minutes, it is 10 liters per second, and then it may increase or it may decrease. If it is varying, then we call it as a transient flow. But if it is a steady state flow, in general, we tend to find out the discharge and then multiply with its density to get the mass flow, steady state mass flow. Okay. Now, what can be the very simplest or crudest or the accurate method by which we measure the flow rate? Okay, you are having a channel or a tap through which water is getting flown. So if at all somebody asks you to find out what is the flow rate or in a laboratory purpose, so what is the way that you calculate if it is a non-volatile liquid? That means it is not vaporizing when it is exposed to the environment or the ambient conditions. If it is not getting evaporated, for such a liquid, what is the crudest method or the most accurate or standard method by which you measure the flow rate? What can be that? Suppose there is a channel through which the liquid is flowing. So how do you want to estimate the flow rate? The simplest method is take a measuring flask where the flask, the volume of the mask is marked on as a scale on the top on the periphery of the flask, and then you have a stopwatch, and then you get the water flowing for how much volume is being collected for a particular time. So if you put that, then you will get so this much of for 10 seconds, this much of liquid is being collected in the measuring flask. That will be your volume flow. So here, what can be the chances for the uncertainties? What can be the chances? What may be the reasons that will create the uncertainty in such a measurement? Is my question clear?
Velocity, sir.
Velocity. Assume that the velocity is constant. Okay.
Sir, uncertainty in the time being measured.
Yeah, uncertainty in the time that you are calculating. It depends on the watch that you are using, whether it is accurate. But mostly your watches are accurate enough because they are precise machines, so they are accurate enough. So while taking the volume of the liquid, collecting volume of liquid in the flask, how do you measure it? Whether you are taking and measuring that on a, after collecting the water, you are keeping it on a table and then making sure that you don't have any parallax error or not. So if you are not looking at the volume properly, then it may lead to some kind of uncertainty. And another thing, as your friend has rightly pointed out, if the velocities are varying slightly, okay, so you may not expect 10 meters per second of flow every time. It may be 11, it may be 10 sometime, it may be 11 again, it may be 10 again. So if there is a variation, what can be done to alleviate that kind of uncertainty? In general, crudely, what can be the simplest thing that we need to do?
Multiple experiment, multiple reading we can do, sir.
If you are doing it for a very short period of time, multiple times if you do, will you be able to overcome that difficulty? We are not 100% sure. You may be, but the easiest thing is take more time for collecting the volume of fluid. Instead of 30 seconds, you take 10 minutes, or you take 5 minutes, or you take 3 minutes. The more the time that you take, the average, the variations that are inside the fluid may be averaged, so that you will not have too much of uncertainty in the measurement of the fluid. Okay, so an accurate measurement of the weight of the liquid collected should be made to find out the mass flow rate. Okay, suppose if you are asked to find out the measurement, you take that volume of fluid and take a proper weighing machine and weigh the amount of liquid that you have collected for a certain period of time, and if the weighing machine is very accurate, then you will directly get the mass flow rate accurately. This much kgs per second you are able to find it. So here the uncertainty may come within the weight and the weighing machine. The weighing machine, what is the uncertainty? So that you have to include to find out the total uncertainty in the measurement. Okay, so this is the crudest method that we frequently employ for calibration of liquid flow meters also. So that means, in general, if you want to use this method for a flow meter kind of a thing, for example, if in a petrol bunk you want to find out, generally the petrol is volatile in nature, so there it may not be useful. But suppose if you are using it for measuring the amount of water that is being supplied to an apartment or a household, a single household, you have a flow meter and you want to calibrate whether the flow rate that is being measured with the help of the device or measuring instrument is proper or not. There you can directly use this crude method. So just collect the amount of water for a particular period of time, and you also look at the reading that you are getting from the measuring device. So how much is the variation? That will tell you that will set up the calibration curve for that flow meter, so that whatever the errors associated with the flow meter can be corrected. So however, this method, this direct weighing technique that we are talking about, is not suited for unsteady flow measurements. As I told you, this is best suited for steady state flow measurement. Okay, so now we will also look at, in this particular module, we also try to look at various instruments which works on different principles, various principles for measuring the flow. Okay, so the basic classification is like this. The first classification is based on the working principle of primary or quantity methods. So you are trying to measure the basic primary or quantity methods. Therefore, by using that, you will be able to find out the flow meter. For that, we generally use weight tanks, okay, and volume tanks, graduated cylinders, bell provers, and so on. These are all the things which are similar to what we have discussed. Okay, weight tanks and volume tanks, graduated cylinders. So the second classification is basically flow meters, mechanical flow meters, where you are using obstruction meters. Okay, we are using obstruction meters. That means we are trying to obstruct the flow rate. We are not having the flow to continuously pass within the same cross section of the pipe. Instead, we are varying the cross section of the pipe. Thereby, we are actually trying to obstruct the flow, and due to the obstruction or change in the cross section of the pipe, there is a pressure difference that is being created, and based on the pressure difference that we are able to measure with the help of other devices, we will try to estimate the amount of flow rate that is happening through the pipe. So such a device, under such working principles of instruments, we have venturi meters, we have flow nozzles, we have orifices, and we also have variable area meters, which is also called as a rotor meter. So we will go one by one about each one of them in the coming classes. Okay, and in flow meters also, we also have another classification, which is the volume flow meters, which is responding to the amount of volumetric flow. So depending on the rate or volume of flow that is passing through the tube, we are using turbines and propeller meters. Okay, we are kind of keeping a rotating element inside the pipeline. So when the flow is happening, the more the velocity of the flow, automatically our flow rate is increasing. So when the velocity of the flow is higher, this obstruction propellers or turbine meters, they will rotate with higher speed, and the rotation of these propellers or turbines is directly proportional to the velocity of the flow. So the more the velocity of the flow, the more the turbine, and you know the area of the flow of pipe. So therefore, we'll be able to find out the mass flow rate of the fluid that is passing through the pipe. Secondly, we have electromagnetic flow meters, so which works on the principle of electromagnetism. Okay, so here we can measure only the flow rate of liquids, and then we also have vortex shedding meters. Okay, so that we will when we go deep into the subject, we will understand. So for simplicity, I will tell you, you have a bluff body. Imagine that you have a bluff body, right? So we have a circular body like this, cylinder. You imagine that it is a cylinder, okay, which is horizontal. Okay, the 2D diagram I am drawing here. So now there is a flow that comes in. So when the flow comes, it stagnates and then it goes. Similarly, it goes. So when it is going, depending on its velocity, it creates the vortices at the back or rear end of the cylinder. So now what we are doing, so the amount of this vortex formation is what we call it as vortex shedding. Okay, vortex shedding. So the more the circulations that we are creating, the more the velocity, the higher the velocity, the more the vortex shedding happens. Vortex shedding happens. The more the vortex shedding. Just a minute. The more the vortex shedding will happen. So now we have ultrasonic flow meters also. We have ultrasonic flow meters that are happening. In the vortex shedding meters, this amount of vortex formation we are trying to measure with the help of some sensors, and with the help of these sensors, the more the vortex shedding frequency we will find out, and that is directly proportional to the velocity of the flow, and we know the area of the flow. So area into velocity, we get your QR flow. Okay, so this is the example for volume flow meters, one of the examples for device. Next one is ultrasonic flow meters. You may be able to understand what do you mean by ultrasonic flow meters. And ultrasonic flow meters, you will be sending sound from one side, and it may be taking ultrasonic, that means ultrasonic waves you are sending from one thing, and another thing is collecting it. So depending on the flow velocity, so there will be a change in the receivers. Okay, initially it is supposed to receive like this, because the more the velocity, the particles will scatter this wave, and it takes time to come to the transmitters, to the receivers from the transmitters. So the change in the phase phase of these signals will help us to find out the velocity of the flow, and that we will use to find out the velocity that we find out from this, we will try to use for finding out the volume. And the next one, which is very important one, is the positive displacement meters. You are finding it out that it is positive displacement meter. So what is happening over here? We have this pipe and we are trying to obstruct the flow with the help of certain devices. Okay, what these devices will do is they will allow only a fixed amount of the fluid, every time or every second, and because of this velocity, they keeps on rotating. So every time out in the outlet, we have fixed amount of fluid that is coming. Okay, but the rotations that are happening, it depends on the velocity of the fluid. Okay, if it is only 10 liters per second, this is every time it is sending one liter, so it will rotate per second 10 times. Suppose if it is 100 liters per second, okay, in a second this meter will rotate 100 times. So there is a counter mechanism to find out the rotations of this particular axis of this device and how many rotations does it make. And because every time it only sends out 1 liter, but the number of rotations, how many times it happens, will help us to find out the flow rate. So these are under this category, we have positive displacement. And coming to the advanced flow meters, we have very advanced meters like Coriolis meter, hot venturi meters, and thermal mass flow anemometers, which we are not discussing. It works, the Coriolis flow meters work on the Coriolis principle provided by Galileo. So this is a very accurate flow meter that we use to measure the flow rate. This is one of the most accurate flow meter that is available for today. And those who does have interest, please go through the principles of this Coriolis meter and how critical flow venturi meters and then thermal mass flow anemometers. So these are the recent advances in the flow meter devices. Okay, so now we will go one by one. First we will look at the volume flow meters first, and then we will go to the flow meters, and those are the two topics we are actually concentrating more. We also have velocity probes. For example, as I told you, all these are comes under the same principle, where we are actually trying to find out the velocity, and then we are multiplying the velocity of the flow with the help with the area of the pipe, and then we are saying that it is a discharge. So this is basically your velocity probes. We have pressure probes, like total pressure. In here we are trying to find out the pitot static tube or direction sensing probes. By this we are trying to find out the velocity, and then from that we will be able to find out what is the flow rate. Similarly, hot wire and hot fill anemometers. So where this hot wire and hot fill anemometers will be used. So this hot wire anemometers works on two principles. I will tell you the simplest method. Like you have a small thin wire over here. This is the small thin wire, and for this wire we are actually sending some current through a standard current thing. Okay, so there is a circuit and we are sending through current on a constant constantly. So because of the flow of current, we have some resistance that is being developed. Okay, so because of this resistance, it gets heated up, the wire gets heated up. Okay, now we have kept inside a fluid flow like any gas kind of a thing. So when this fluid flows over this small wire, through which the current is flowing and gets heated up, because of the temperature of this fluid flow, it gets cooled down. Correct? So now when it gets cooled down, automatically your resistance will vary because of the temperature, and therefore for getting the same initial conditions, we have to increase the increase or decrease the current that is passing through. So the amount of current that is increasing or decreasing is directly proportional to the velocity of the flow. So if we know the velocity of the flow, and automatically we can find out the discharge of the flow that is passing over the hot wire. So that is the principle of hot wire or hot film. And then we have Doppler shift methods, just like whatever I have discussed in the previous thing. Like we have a Doppler, how much angle or frequency is changing. So based on that, one signal, how much variation it is happening, it is varying. What is the phase angle that is being changed? Based on that, we will use this Doppler shift methods. And another important and very widely used technique in research is the particle image velocimetry. Particle image velocimetry, or there are certain materials which we will keep into the fluid flow, okay, and that we will track those particles by putting some light or laser lights and all, so that the flow visualization can be done, as well as we will be also able to find out when we are tracing it how much velocity and all, that we can post process and find out through the video that we will take. So we will be able to find out what is the flow rate that is happening through the pipe. So these are basically flow visualization techniques. So that means you're also looking at how the flow is taking place. Suppose if it's a gas, you may not be able to see with our eye. So these particle image velocimetry techniques will be helpful for finding out. And then we also have crude methods like flow visualization techniques like smoke trails and smoke wires, dye injection. So you will try to keep the dyes, colored dyes into the flow, and then you will be able to trace how it is happening. Hydrogen bubble, laser-induced fluorescence and refractory index change, interferometry, Schillerian or shadow graph technique. So these are all comes under flow visualization techniques, so which can be used to determine the flow rates of the fluid. Okay, so these are all the different classifications of the flow meters that are available in the market. For us. So having a basic understanding of these instruments is of very vital importance for you, because you may be doing some experiments in the coming future. If some of you goes to higher studies and all, or if some of you goes to the industry, process industry also, it is one of the key parameters that is being monitored in the industry. So having a basic understanding about these flow meters is of utmost importance. Now let us start with the flow meters, like positive displacement flow meters. So there are many types of positive displacement flow meters. So what we are trying to do in a positive displacement flow meter, the very working principle is, it measures the volumetric flow rate of a moving fluid or gas. So there is a pipe, and in which the flow meter is happening. So what we try to do is, so this is the pipe. So initially this is the pipe. Now what I'm trying to do is, I will be cutting and having this kind of this meter. Let us say this meter I am trying to include into the. Okay, just assume that this is the device. Okay, so I am trying to connect this. Imagine that this is a connection. Imagine this is a connection. So for a pipe, continuous pipe, I am fitting this device, okay? And what I am trying to here is, I am trying to find out the flow rate of the moving fluid or gas, both. It can work with both liquids and gases. By dividing the media, whatever the flow that is coming in, that amount of fluid, I am dividing it into fixed meter volume. So I am not allowing the full fluid to go into that. At a time, only a fixed amount of fluid I am allowing to pass through this device. Okay. For example, this pipe may be capable of sending 10 liters, for example, and so the flow rate is 10 liters per second, for example. But what I am trying to do is, by fixing this meter, every time I am allowing only 1 liter. For example, it can at a time send 1 liter. So that means one complete revolution of this inside this will only send 1 liter. But per second, it will rotate 10 times. So that is the fundamental. So we are not allowing the continuous flow, but we are dividing the fluid into certain fixed or metered volume of the flow to exit through the meter. And how much time for a particular unit time, how much amount of this fixed meter volumes it is able to pass through it is what we are measuring by means of certain sensor or a geared or a metering device. We will try to measure, and through that we will be able to find out the amount of flow that is passing through the pipe. It generally consists of a chamber. It have one chamber, and that actually obstructs the flow. We will have certain chamber, then that actually obstructs the media flow, and we tend to have a rotating or reciprocating mechanisms inside this particular chamber, which allows the fixed volume amounts of fluid to pass. Okay, so if we obstruct it, either we will put the arrangement as reciprocating like this, or it is a rotary kind of an arrangement, such that the whole volume of fluid is only is allowed. Only a fixed amount of fluid is allowed inside each time, and that is being exited through the end of the pipe. So the number of parcels, you can understand the number of parcels that passes through the chamber determines the medium. As I told you, the number of times the fixed amount is passed through it will tell you the total volume. So the rate of revolution or reciprocation is what it will determine the. Okay, so that is the basic working fundamental principle in this positive displacement flow. So these are very precise instruments, and since we have called them precise instruments, so the inside part we will have very precise arrangement, fabrication techniques is required. So the internal moving components like the reciprocating parts or the rotary parts, they are hydraulically locked in tandem with the volume of fluid. So there may not be any chances for the leakage of the fluid to happen, or since we are holding down a fixed amount of fluid. For example, we will come to know that once you see that. For example, you have this lobe kind of a thing. So every time the liquid comes in, for example, this is the inlet that is connected, and for example, this is the outlet. Okay? So every time this comes in, fills this particular chamber, and this will apply force, and while it is moving, it will pass through it. So the next chamber will come over here, and it will rotate, and that's the same thing. So now this fixed volume of liquid should be equal to this fixed volume, and that should be equal to this fixed volume, and that should be equal to this. So that is what we have to fabricate very, very carefully. So there should not be any variation between this volume and this volume. So then obviously you are going to get error if there is some difference in the volumes. Okay, so it also measures intermittent flow, very low flow rates, and liquids of almost any viscosity. One of the problem in measuring the flow rate is viscosity. This is one of the biggest problem that will be created by the fluid flow. For example, if you take water, it doesn't have a lower viscosity compared to grease or some kind of paint. You take any paint for householding, you will take. Suppose nowadays we have got these instruments to paint. Initially, earlier they used to have these brushes, take the paint, and then they try to paint it over walls and all. Now we have these sprayers that have come, correct? So we have got the paint, we will keep it into it, and then we will spray it. Now what is the challenge? Why earlier it was not done? Because earlier we need to pump that liquid. So we need to apply force to push that paint out of this nozzle. So nozzles are very small area volumes. So if it's water, very less amount of force is required. But when it comes to these paints and greases, it requires a very huge amount of force because of its viscosity, because of the internal frictional forces that is associated with these paints and all. You tend to apply more and more amount of force. So the liquid flow is tremendously affected by the viscosity of that flowing fluid. So that is one of the. So for any measuring device, we will always ask the vendor, if you are asking for a flow meter, we will ask you what is the liquid that you want to use and what is its viscosity. So this is one of the governing parameter in the measurement devices for the working principle. So viscosity forms one of the important parameters. So, and this positive displacement flow meters, the best thing with this is any viscous liquid of any range can also be measured with the help of this positive displacement flow meters. It instantly moves when there is fluid motion. So we don't need to give any external energy. When there is fluid flow and this device is connected to the pipe, it immediately moves. And whenever there is no passage of fluid, it immediately stops. That is the best thing associated with the positive displacement flow meters. So what are the types of positive displacement flow meters we have? So we have a reciprocating piston meter. Second one is the gear meters. The third one is nutating disc meter, and fourth one is rotary vane meters, and finally we have this diaphragm meters. Okay, so these are the 5 different types of flow meters which are available under the classification of positive displacement. So let us have a look at the reciprocating piston meters. You can see over here. So we have an inlet. Okay, we have an inlet here. We have an inlet here. Okay, so this is the pipeline. This is the pipeline, and into the pipeline I have connected this piston meter. So this is the piston meter, where you can see that this is the reciprocating piston meter that is available here. Okay, you can see here there is a central chamber which is connected eccentrically. It's not at the center. So the rotation of this shaft, okay, here, whatever the rotation that is happening, the eccentrical thing, this eccentrically moves all the 4 valves simultaneously. Okay, so when it is trying to move from here to here, this will move to the right, this will move to the right, this will move to the bottom, and this will move to the bottom. And when it is trying from bottom to top, these 2 will move up and these 2 will move to the left side. So simultaneously we are working with 2 things. One is the horizontal will move right side to the left side, and the top and bottom valves will move to the top or to the bottom depending on the rotation of this eccentrically connected lever at the connected lever. So that is what the principle is. So every time this is connected, the simplest working principle is the water will enter, and only because of this force of this liquid, only a fixed amount of liquid is always allowed to pass. So whatever the liquid chamber that is there, this is here, this is all the same amount of mass flow rate. So every time it at any instant of time, it only passes, whatever be the flow rate, it passes only a fixed amount, but per unit time it is able to completely send whatever the flow rate that is passing in terms of fixed amounts of that. Okay, so the number of rotations of this shaft is being noted down with the help of some sensor. So that sensor will calculate the number of rotations it has made, and we know for each rotation how much liquid it is able to pump. So multiplying the number of rotations with the volume of the fluid that it can pass through in one complete rotation will help us to understand the amount of fluid that is passing through the amount of flow rate that is passing through the pipe. So I am showing the animation here. You just have a look at this, how it works and all. So
size pieces. Each rotation allows the same amount of fluid to pass through the wheel.
So you can see here that is
piston displacements is not affected by the fluid's viscosity, density,
So
or flow profile.
you can see here these 2 valves are moving simultaneously to the top or bottom, and these two walls are moving to the left or right simultaneously. And we do have certain passages over here. Depending on the flow, this will be pumped through outside. Just have a look at this video. It is self-explanatory, and I hope you are able to listen to the audio. Is it audible or not?
Yes, sir, audible.
The video voice is also audible, right?
Yes, sir.
Liquid enters through the base of the meter and it travels into the center cavity below the base of all the pistons. As the meter rotates and moves one of the pistons forward, the porting tube is connected to the center of the meter. This allows the liquid to flow down the tube and displaces the adjoining piston. As that piston reaches the end of its travel, the porting tube is sealed off from the center of the meter and connected to the exhaust port. Each piston has its own exhaust port that is connected to the outer ring in the meter's base. Fluid collects in this ring and exits through the meter's outlet port. Each piston carries over a known amount of liquid from the inlet to the outlet side. The pistons act as valves and displacement devices. By connecting them to a central crankshaft, the pistons are sequenced to continually divide up a flowing stream into known-sized pieces. Through the use of a precision encoder, crankshaft's rotation is good to a high-resolution electrical signal, which can report the flow with high accuracy and repeatability.
So I'm again playing the same thing. Then
Size pieces. Known-sized pieces. Each rotation allows the same amount of fluid to pass through the meter, with the added benefit the sum of the four piston displacements is not affected by the fluid's viscosity, density, or flow profile. Liquid enters through the base of the meter and it travels into the center cavity below the base of all the pistons. As the meter rotates and moves one of the pistons forward, the porting tube is connected to the center of the meter. This allows liquid to flow down the tube and displaces the adjoining piston. As that piston reaches the end of its travel, the porting tube is sealed off in the center of the meter and connected to the exhaust port. Each piston has its own exhaust port that is connected to the outer ring in the meter's base. The fluid collects in this ring and exits through the meter's outlet port. Each piston carries over a known amount of liquid from the inlet to the outlet side. The pistons act as valves and displacement devices. By connecting them to a central crankshaft, the pistons are sequenced to continually divide up a flowing stream into known-sized pieces. Through the use of a precision encoder, crankshaft's rotation is converted to a high-resolution electrical signal, which can report the flow with high accuracy and repeatability.
okay, so we are using the encoders, electronic devices, which are called as encoders, which actually helps in calculating the number of rotations, the RPM of these shafts. We can also use tachometers at the end of the axis, and you also can find out manually also. But in general, that is not possible to do manually all the time. So in general, we will have these electronic encoders to measure the rotations of the shaft. So this is also another example for gear meter. You can see here, it's a very simple thing to understand. That may be a little complex to understand. You can see over here, we have a gear meter, and this is the gear meter that we are using. We are using to measure the flow. Okay, there is a certain amount flow rate that is passing through the inlet, and you can see that your very precisely machined two gears are connected. Okay, so lobes are connected over here. This particular. So now one end of this connected to the pipe. Okay, this flame is connected to the pipe. The help of proper sealing and all. This is the element. The top is also covered actually. So now through the pipe, a certain amount of flow rate will enter, and it tries to rotate this particular gears. So you can see here, when it is rotating, it only allows only a certain portion of the liquid through this, for the first half. So that will move out, and then a certain amount of liquid only passes through this. Okay, so when it is rotating, only a small amount of fluid that is entrapped in between these gears is allowed to pass every time. So one time to the top of the lobe, another time through the bottom of the lobe, the fluid will pass out of the tube. And the number of rotations of these two gears we will be able to measure with the help of the encoders, and that is how this gear meters will work. So since we have used gears, it is called as a gear flow meter. Now have a look at this this particular animation.
As this simplified illustration shows, there are two oval gears inside of the meter. The flow of the fluid causes the gears to rotate. As they rotate, specific amounts of fluid are trapped in the chambers between the gears and the meter body. So each time the gears rotate, a precise amount of fluid is passed along. If the flow increases, the gears speed up, but they still pass the same precise amount of fluid along with each rotation. A counter mechanism counts each rotation of the gears to determine the total flow of fluid through the meter.
This is what I'm calling it.
Another example of a flow meter that measures flow directly is this nutating disc meter. It gets its name from the action of the disc.
Now we are also looking at the nutating disc meter. This is another example of the positive displacement flow meters. So here there is a nutating disc, that means it wobbles top to bottom. You can see it will move through this direction to only this direction. So it wobbles through because of the flow in that is coming in, and this wobbling is being measured with the help of this encoder to measure how many times it wobbles. But every time it will only a fixed amount of fluid pass out through the meter. You can watch this animation.
Which can be seen here. The word nutate means to wobble or roll about an axis of rotation. During operation, the disc rotates much like a slowly spinning top. As the disc rotates, specific amounts of fluid are trapped above and then below the disc. An increase in flow will cause the disc to rotate faster, but the same amount of fluid will be passed along with each rotation. The nutating disc meter counts the precise amounts of fluid passing through it to determine total flow.
Okay. So this is one of the example of the nutating disc meter. You can see here the example I have given. The fluid that is coming in, passing through this only on the top, and because of the amount of fluid it wobbles, and you can see here from here, this side, it is coming and it wobbles, and every time it is passing through it. Depending on the more the velocity, the more it wobbles, and how many times it is wobbling, you can see this black color thing that will actually measure this. Okay, so this is the working principle of this nutating disc meters.
Water flows directly into the meter housing. The water first flows through the meter's internal strainer before it enters the measuring chamber. The strainer protects the measuring chamber from damage due to debris in the water. Inside the chamber assembly is a movable disc that's located on a sliding ball guided by a thrust roller. As the water flows into the measuring chamber, it causes the disc to nutate, a motion similar to a coin dropped on a table. Notice that the disc does not rotate, but rather wobbles on its axis. Therefore, the space formed between the disc and the chamber wall has a constant volume as it moves around the chamber. The water in the chamber is a fixed volume, or displacement. That's why a disc meter is called a positive displacement meter. The smooth motion of the disc also eliminates the annoying noise produced by some other types of positive displacement meters. As this happens, the nutating disc translates its movement through a magnetic coupling to the register. The water then leaves through the outlet port of the chamber assembly.
Okay, so that is about the nutating disc meter. And the fourth one is the rotary vane meter. Okay. Here you can see here there is an inlet. The pipe comes in. There are spring-loaded vanes. We call it as spring-loaded vanes. That means you can see here the cross section is not uniform. Okay, so when it is rotating, these vanes are rotating. Depending on the cross section, it adjusts itself. Then it is a tight seal. Suppose the liquid that is coming into this particular volume, the fixed volume of liquid will be only sent out because this is getting adjusted. When this if you see here, this vane is of higher length, but when it comes to here, it is a shorter length. because of the spring, it is able to adjust. But every time only it allows a fixed amount of fluid through the vein. So the liquid enters here, this fixed amount, and then it translates and it allows to pass to the outlet. So this is basically the working principle of the rotary vein meters. And the final thing is the diaphragm meters, which we will see in the next class. Already time is 11 o'clock. So we will discuss about this diaphragm meters in the next class. So any doubts up to this, you can ask me, or I will send you this, I will share this PPT with you. So have a look at the animations that I've sent. And still, if you find it any difficulties or anything to discuss, you are free to discuss. Any questions I would like to take?
Sir, can you show the slide of gear positive displacement flow meter?
Gear?
Geared one, sir. Geared. There.
Okay. Others who doesn't have doubts or want to attend another thing, you can go to your particular. You can leave the session.
As this simplified illustration shows, there are two oval gears inside of the meter. The flow of the fluid causes the gears to rotate. As they rotate,
sir, you are not presenting the screen.
Oh, sorry.
As this
Sir, the
simplified
previous one.
illustration shows, there are
You are
two
asking
oval gears
reciprocating
inside the
gears?
meter.
Are you asking
The flow of the
reciprocating?
fluid causes the gear.
This is rotary gear meter. You are asking this?
No, sir, the next slide, 10th one.
Yeah, this one.
So what is the difference between the oval and circular gear we are using?
Nothing, but it only changes the volume, nothing more. If you have a oval shape, the amount of volume will be different. If it is a circular thing, the volume will be different. There's not too much of a difference with that. Each time, how much volume you want to have, that will be.
Sir, if the flow is very high, like suppose at a stretch flow comes, so means from the it can flow centrally towards the flow meter, sir. So it may obstruct the rotation of the gears also, sir. Like it may some regime of flow may strike at the directly at the center, so it may obstruct the rotation of the gears.
In circular flows, that you are talking about circular gears, probably.
No, sir, I am asking about this oval gears.
In this oval gears, so the fluid that may comes in, you are saying that it hits at the center. How there will be a rotation? Is that the question? Is?
Yes, sir. Means directly if they strike off the gear teeth, then it will means obstruct. Therefore, you said, it may.
Why it will obstruct? You can see here that the amount of fluid that comes in and hits this particular gear first. So immediately it will rotate. So there is a small amount of fluid that gets entrapped in this particular thing, and it hits. While hitting, it will whenever there is a chance for the fluid to pass through, whenever it has some opening, it immediately passes through it. For example, in this green colored thing you see, the liquid will come over here, okay, and it hits whatever the small passage that it is having. It tries to leave through that passage, even though it is applying some force, and it tries to move through the small opening, whatever that is available in there. So if you look at this too, at the center, there's a perfect obstruction. So there is no flow that passes through it. Okay, it's in a 3D. If you see, that is complete here. You can see here. It's a perfect obstruction. Each time there will be perfect mating. So you can never have any fluid that is passing through the center. Only through the spaces provided in here and in here. Through that only there is a passage of fluid. So every time how much amount of fluid that is passing through, we can measure it. For one complete rotation of this particular gear, how much volume of fluid you can measure by means of one rotation you can make, and you can measure through a standard volume flask and weighted method, or whatever method that you can use, you can always calibrate that. Over a period of time, the only problem that comes with these kind of meters is, so there will be this friction. So over a period of time, there may be, as you rightly pointed, there may be certain wear and tear and some leakage may happen, and because of that, instead of whatever we thought the fixed amount of fluid is coming out for one rotation, it may increase. So for that, this kind of instruments always required to be calibrated first. Okay, so fixed amount of fluid, fixed measured amount of fluid is passed through this particular disc for one rotation, and see whether that the measured amount is passed out or not. Okay, so that's how they will try to find out this calibration and then do it. Initially, in the case of working principle, there is a proper locking that will happen. So therefore, you will not have any leakage through the center, because whenever the liquid is there or fluid is there, it always takes the least resistance path. Okay, so you have a least resistant path over here. So always it tries to push through it rather than going through the center. Is it clear?
Yes, sir. Sir, another doubt, sir.
Yeah.
Sir, will there be a cavitation, like due to high velocity of flow? Will there be
cavitation?
Yes, sir. Cavitation, sir. Problem of cavitation.
Cavitation will always be there, because if there is very high velocities and all, there will be that chances will always be there. That's why your selection of the casing or the gauge. So those are paints that you use. We try to have as low cavitation as possible, because this is a closed sealed thing, because we don't want the water that we are measuring that may have a lot of impurities and all. That's why we are protecting it through a casing and all. Therefore, it's generally sealed thing. So obviously cavitation we have more chances to happen, but that can be negated by the use of these paints and other things. So the rust and all we will see, but these kind of instruments definitely over a period of time will have their own problems. All the mechanical devices will have their own problems. Okay? So but however they will be always try to be calibrated and get very approximate method, very what we call precise measurements. You need to have this calibration done every month or every 15 days. They will do that. In industry, it is not that you once fix it, you will continuously measure. They will time and date, they will have this inspection dates and all, where they will try to keep on measuring these things. That is what this quality checking people and all, they will maintenance people, they will all look at these aspects of that. Okay, so cavitation will happen. It's like a pump only, no, nothing more.
Yes, sir.
Just trying to pump. Instead of initially, if it is a pump, generally we provide the input energy. Here there is the fluid energy is converted into the input. That is what the difference is. So ultimately the principle is the same. But for
Yes,
very
sir.
high velocities, it will have. Any more questions?
No, sir. Doubt, please.
Anyone? Any other? So as I told you that Coriolis flow meter is a very interesting flow meter. Those who have interest and are not for the sake of the exam, please go through that and look. And one more thing is, A section sir, Satyanand sir has called me yesterday and told me that many students have actually copied in the some of the questions, and he has given, that means the same answer while writing the answer. If suppose 0.1 has to be put in the answer, instead we found out the answer to be 0.01 somewhere. And if everyone copied the same thing, he has given 0. And he requested me to be consistent with that. So probably I will also follow the same thing. Do you understand what I'm saying? Suppose in the first problem, the resistance problem, suppose somewhere R1 is 0.1, but the key or wherever you found out, if someone has taken 0.01, which is not given in the problem, but so if 10 people copied the same 0.01, he has given 0 marks. So I'm also going to take, he also requested me for uniformity. He asked me to follow the same thing. So probably I will also follow the same thing. All right. Most probably this weekend, Sahil, I will try to finish this weekend. Any urgency is there? Tell me so that I will try to finish it within today. I think I can take time up to Saturday or Sunday. Is that fine? Okay. Thank you, sir. This weekend and maximum I will give. At the most Monday. Okay. So that I can slowly correct and I will not rush. So again, we have a class on Friday, right? In between, do we have any chance? Please let me know one day before so that we can finish that. Alan, I hope you have taken the attendance.
Yes, sir.
Okay. Okay, guys, if you have no doubts, then I will wind up the session. Thanks for attending this particular class. So please go through the session. We'll share the recording as well as the PPT now itself. So please go through it. Okay? All right.
Thank you, sir.
Thank you.